Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. So, as you can see, we are going to discuss in this video presentation ocean heat content. So, here we go. But first, a list of the metric prefixes. You may find this handy. You may want to, go full screen on your device, take a screenshot, and you've got all the prefixes that use in the SI metric system readily handy. So why did I include this? Because we're going to be talking a lot about zeta joules in this presentation. So as you can see here, no prefix means 1, which is 10 to the 0. So basically these are powers of 10. So if we look at smaller than 1, the deci is 10 to the minus 1, that's 1/10. Centi, 10 to the minus 2, or 1 over 100. And milli is 10 to the minus 3. Micro, 10 to the minus 6. Nano, 10 to the minus 9, etc. Okay. And once you get to the milli, or in the opposite case here, kilo, then we increase by powers of 3. So you go 3, 6, 9, 12, 15, up to 24, right, plus or minus. So on the positive side, deca is 10 to the first. Then you have hecto, 10 squared. Then you get the kilo, 10 cubed. Mega, 10 to the 6th. And of course, these are the symbols. And then giga is 10 to the 9th. Tera is 10 to the 12th. Then you have peta, exa, zeta, iota. We're going to be talking a lot about zeta, which is 10 to the 21. When you look at papers discussing heat, be it in the atmosphere or in the ocean, the two units you commonly see are tera, 10 to the 12th, and zeta, 10 to the 21st. Okay, so there's a list of your metric prefixes. Oh, what is a joule? There are several uses of joules. You can use them from work, kinetic energy, heat energy, electrical energy, just to name a few. For purposes of this presentation, I'm going to basically concentrate my comments to thermal energy. So a thermochemical calorie is equivalent to 4.184 joules. Capital J is the symbol for joules. One international table calorie is 4.1868. Similar slight differences. The first two decimal places are the same. It differs afterwards. Then you have 1 watt hour is 3,600 joules, or 3.6 times 10 to the third joules, or 10 to the 3, 3.6 kilojoules, right? Kilo, 10 to the 3. You can substitute that in. 1 kilowatt hour, 3.6 times 10 to the 6 joule, or 3.6 megajoules. Again, mega, 10 to the 6. Then 1 watt seconds equal to 1 joule. The heat required to raise the temperature of 1 gram of water by 0.24 degrees Celsius is 1 joule. Okay? So there's a conversion right there. You need 1 joule applied to 1 gram of water. You do that, and you increase the temperature by that amount, 0.24 C. A non-dietary calorie used to be the unit of heat energy used. It is defined as the amount of heat required to raise 1 gram of water 1 degree C. Okay, this is calories. A kilocalorie is the amount of heat required to raise 1 kilogram of water 1 degree C. Now, the amount of heat required varies depending on the starting temperature, what the atmospheric pressure is. Lower atmospheric pressure does not require as much heat energy to increase temperature. Higher atmospheric pressure, higher energy requirements. Generally speaking, let's consider the following. It takes 4 calories to raise 1 gram of water, 1C, or 4 kilocalories to raise 1 kilogram of water, 1C. It takes 80 calories to melt 1 gram of ice into water, or 80 kilocalories to melt 1 kilogram of ice into water. Okay, so far, okay, I'm just talking about calorie. And I'm saying calories defines heat raised 1 gram of water, 1 degree C, or 1 kilogram, 1 degree C. And now I'm telling you that it's 4 calories to raise 1 gram of water at that 1 degree C, or 4 kilocalories to raise that 1 kilogram, of water, 1C. Now let's take the 4 calories or 4 kilocalories. I'm going to use the kilocalories now. Let's take the 4 kilocalories. Let's take the 80 kilocalories, and let's convert that into the equivalent amount of joules. So 16.736 kilojoules is needed to raise 1 kilogram of water, 1C. 334.72 kilojoules is needed to melt 1 kilogram of ice. Okay, it takes considerably far more energy to melt ice, 20 times, than it does to raise the temperature of water, 1C. Think about that in terms of all the ice melt going on around the world. Greenland, Antarctica, alpine glaciers, etc., right? So now you're melting all that ice. Think how much ice has melted, the mass of that, and then think about using this calculation right here, how much energy that has been, how much energy it took to do all this melting, which continues on. Okay? So think about that in terms of all the ice melt going on, as well as the now continuing heating of the ocean. It takes a lot of energy to melt the ice, but once that ice is melted, the same energy used to melt the ice now raises the water temperature. But it doesn't take as much energy to raise the water temperature. So that's if it took 334.72 kilojoules to melt 1 kilogram of ice, I now have, where I had 1 kilogram of ice, I have 1 kilogram of water, and I apply 334.72 kilojoules to that, I'm going to do what? I'm going to increase the temperature of that now 1 kilogram of water, 20 degrees C. So now think about that. Oops, excuse me. So the same energy used to melt the ice now raises the water temperature considerably more, indicates how much energy was absorbed to melt all the ice. So I'll pause here for a bit so that you can let what I just shared with you kind of marinate in your brains there for a moment or so. It gives you an idea how much heat energy humans have put into the atmosphere. Okay, continuing on. I want to discuss latent heat versus sensible heat. Latent heat is the energy absorbed by or released from a substance during a phase change from, say, gas to a liquid, liquid to a solid, or solid to a liquid, liquid to a gas, so forth. If a substance is changing from a solid to a liquid, for example, the substance needs to absorb energy from the surrounding environment in order to spread the molecules out into a larger, more fluid volume. If the substance is changing from something with lower density, like a gas, to a phase with higher density, like a liquid, then the substance gives off the energy as the molecules move closer together, losing energy because the motion and the vibration decrease. Basically, temperature is really a measure of the energy in a system. the more energy you put in it, you're going to increase the motion of the atoms, molecules, and their vibration. They're going to move further apart, and so forth. And that is measured by your device called a thermometer. So that basically the temperature is measuring the energy in the system. Now, water vapor is a greenhouse gas located in the atmosphere and a very important component for cloud formation. We all know that. If the air is dry or unsaturated, clouds are not likely to form because there is minimal water vapor in the air. If the air is moist or saturated, the water vapor will condense to form clouds. When these gas molecules condense into liquid drops, latent heat is released into the atmosphere, which warms the air surrounding the molecule. This helps to add instability to the atmosphere, and this warm air surrounding the molecules want to rise. Warm air is less dense than cold air because the molecules in warm air move around much faster, move further apart, and at latent heat, that was basically what we're describing here, right? That latent heat plays an important role in thunderstorms and hurricanes. Clouds form when warm air rises and water vapor condenses onto particles called cloud condensation nuclei. At that point, the air is saturated. When the air first begins to rise, the water vapor is in the gaseous phase. When the water vapor condenses to form clouds, it releases that latent heat into the atmosphere. The latent heat then warms the surrounding air, causing instability. And then that warm air around the droplet will want to rise and condense. This increases cloud height. And depending how unstable the atmosphere is at that point, thunderstorms could form. And then the thunderstorms release enormous amounts of latent heat, which adds even more instability. Sometimes the thunderstorms become very severe. In hurricanes, latent heat is released within the clouds of the hurricane, warming the air inside the clouds. Hurricanes feed off of this latent heat release because it causes instability within the cloud. Warm air will want to rise. The storm will then intensify or gain strength. This is why, as we warm the surface, the surface waters in the ocean, well, these cyclones, hurricanes, whatever you want to call them, typhoons, they're just sucking up all that heat energy, leading to more instability, leading to more energy being released. And this is why hurricanes are becoming stronger and bigger and packing a much bigger wallop, releasing a shitload of energy. I mean, we're now seeing more of Category 4s and 5s. And at this point, you might have to start creating a Category 6 because some of the storms have very high winds. Latent heat energy plays an important role in melting ice. Land ice absorbs heat from the atmosphere or from any underlying liquid body. Sea ice absorbs heat from the atmosphere and the ocean, changing ice into liquid. This is why I take, for example, Antarctica. Okay, you've got heating from above melting the ice, but then you have the warming oceanic waters coming in underneath the ice, melting the ice from underneath. So you have a two-pronged system going on here. So to recap latent heat, it's the heat required to change the phase of a substance. Solid into liquid, liquid into gas, or the other way, gas into liquid, liquid into solid. When going from solid to liquid to gas, it's absorbing energy. When going from gas to liquid to solid, it releases energy. What's sensible heat now? Sensible heat is the energy required to change the temperature of a substance with no change in phase. So that's basically, you have liquid water, you warm up the liquid water. You have gas, you warm up the gas. You have solid, you warm up the solid, but not to the point where it starts to melt into ice. The temperature change can come from the absorption of sunlight, by the soil, by the air itself. It can come in contact with warmer air caused by the release of latent heat by, say, direct conduction. Energy moves through the atmosphere using both latent and sensible heat acting on the atmosphere to drive the movement of air molecules, which create wind and vertical motions. Well, latent and sensible heat also moves through the oceans, helping drive currents, vertical and horizontal, in addition to pressure gradients, thermohaline flows, the density currents, and so forth. Wind stress, meaning a whole bunch of mechanisms by which currents, vertical and horizontal, take place in the ocean. But, latent sensible heat is a part of the deal. Because of the change in phase, this is why more energy is needed to melt ice than to increase water temperature, because it comes down to latent versus sensible heat. Little reminder, right? 20 times more energy to melt 1 kilogram of ice than to raise 1 kilogram of water 1 degree C. Okay, now let's define ocean heat content. In oceanography, climatology, ocean heat content, OHC, and no, it does not mean overhead cam for you auto mechanic folks out there. Okay. Ocean heat content is a term for the energy absorbed by the ocean, which is stored as internal energy or enthalpy. Notice the spelling. This is not entropy. This is enthalpy. Changes in the ocean heat content play an important role in sea level rise because of thermal expansion. Ocean warming accounts for 90% of the energy accumulation from global warming between 1971 and 2010, basically that 40-year period. This actually turns out to be that the oceans have absorbed 93% of the energy humans have put into the atmosphere from burning fossil fuels in this 40-year period. So now when you think about how much energy has already been applied to melting all the ice, warming the atmosphere, warming the oceans, that accounts for only about 7% of what we burned in terms of fossil fuel. The other 93% has gone into the oceans. So the oceans right now have been saving out bacons, but there's a limit to that, because with increase in water temperature, solubility of gases decrease, and at some point, saturation of the gases will take place such that no more CO2 can be absorbed by the ocean, and for that matter, any gas, oxygen as well. And eventually, the warming continues, the CO2 and the oxygen, any other gases, but the CO2 that is already in solution in the water will outgas back into the atmosphere. And by the way, increasing water temperatures, decreasing gas solubility is affecting larger organisms that require dissolved oxygen, because now they're not getting enough oxygen for their energy needs. And I'm thinking of organisms such as homeothermic sharks, such like the great white, tunas, marlins, those kind of fish species that are basically homeotherm. They have a constant body temperature. That means there's a higher metabolism, which requires more oxygen. They're getting stressed out. So ocean warming accounts for 90% of the energy accumulation from global warming in those 40 years. About 1/3 of that extra heat has been estimated to propagate to depth below 700 meters. Expansion, ocean warming contributes to an increased rate of ice melting in the fjords of Greenland and Antarctic ice sheets, plus melting of sea ice in the Arctic Ocean and sea ice surrounding Antarctica. Warmer oceans are also responsible for coral bleaching. Side note, along with the increased CO2 levels creating carbonic acid, that needs to be mentioned as well. Okay. What's enthalpy? Funny you should ask. Here it is. Enthalpy is a property of a thermodynamic system defined as the sum of the system's internal energy plus the product of its pressure and volume and the sum of its potential latent and sensible heat energies. It is a convenient state function standardly used in many measurements in chemical, biological, physical systems at a constant pressure. The unit of measurement for enthalpy in the International System of Units, SI, is the joule. This is why we no longer use the calorie. We use joule. For a given depth layer, ocean heat content, OHC, is defined as the volume integral of temperature multiplied by seawater density and the specific heat capacity with units of joules. Okay, so here's a nice little formula. Ocean heat capacity is equal to rho times C sub P times this triple integral going from H2 to H1. H2 is the lower depth. H1 is the upper depth. Doesn't always have to be the surface, by the way, but in a lot of cases it is, but not always. Then we're going to multiply by theta, which is defined as conservative temperature. And then we have dx, dy, dz. Okay, rho is seawater density. C sub P is typically a constant, the specific heat of seawater. Already defined H2 and H1 is the lower to upper depth. Okay, I've already defined theta as the conservative temperature, which is derived from in situ temperature, absolute salinity, and pressure. And then we have dx, dy, dz. Now, I could have easily written this as d capital V, basically being d volume, because the triple integrals would be your three dimensions, x, y, z. I could have written as dv, but I wrote it out this way. And by convention, when we write out multiple integrals, okay, this one on the far right, you might have a function written here, what have you, for your limits of integration. But this far right integral goes with the variable on the far left. So this one on the right goes with dx. The middle goes with the middle variable. So the middle integral here goes with dy. And the one on the left goes with the one on the right. So like inner, middle, and outer. That's the convention that we write this. So each of these integrals would pertain to a specific variable. Kind of reason why I wrote it out, dx, dy, dz. So now, continuing on, conservative temperature, theta, is a thermodynamic property of seawater. It is proportional to the potential enthalpy. Okay, that's the, as defined up here. And is recommended as a replacement for potential temperature as it more accurately represents the heat content. Integrating this density over an ocean basin or entire ocean gives the total heat content, and we'll look at that in the following figures. Before we do so, let me explain to you what is meant by potential temperature. In the olden days, when we wanted to find out what the temperature profile was in the ocean, we used to lower typically what's called a Nansen bottle. It was basically a cylindrical tube. You lower it to whatever desired depth that you have. You drop a weight. The weight trips mechanisms that releases these things that seal the top and bottom of the tube, thus trapping a sample of water at the depth. You then bring that up to the surface, and you're going to measure whatever it is you are interested in measuring. Usually one of those is temperature. Well, you're bringing it up from depth. As you're bringing it up, the temperature is actually going to be changing ever so slightly, but it changes nevertheless. So when you measure it at the surface, that is a potential temperature of what it really would be at depth. So you have to make adjustments. You have to do conversions. And basically, this conversion is in essence accounting for water pressure. Because when you're at depth, there's a pressure on the water from the overlying, the rest of the water column above it. Now, most people think that water is incompressible, because you can't compress water. And in a lot of cases, especially in shallow water oceanography, that assumption holds, and it's okay to proceed with. But when you get really down to very deep depths, there is a slight compressibility to the water. Not much, 1 or 2%, but it's there. And you have to account for that. And so basically, if I have a given amount of number of molecules, and then I compress that, I'm putting the molecules into closer contact. I'm doing what? I'm increasing their interaction, their collisions with each other. That gets translated as an increase in heat. Notice the temperature will go up ever so slightly. So we have to account for that. So that's why now with the modern equipment, we can measure the temperature directly at depth, accounting for pressure and a salinity and so forth, so that we get basically an accurate temperature at that depth. That's why we now use conservative temperature as opposed to potential temperature. So you don't see potential temperature in the literature anymore. This use of conservative temperature kind of started coming into vogue, about 5-10 years ago, something like that. But it's more accurate, and it allows us to better analyze thermodynamic properties, better analyze if we're looking at thermal halide circulation, for example. So it's I just mention it here because if you to look at older papers, you will see the temperature reported as potential temperature. So, and by the way, if you look at my salinity video, I describe in there all the conversions and adjustments that are used to obtain the salinity measure. Salinity is not usually measured directly, but is inferred from other measurements using conversions and so forth. If you want more information on that, please watch that video. I do a deep dive on salinity. Okay. Ocean heat content can be estimated using temperature measurements obtained by Nansen bottles, Argo float, ocean acoustic tomography, CTDs. CTDs are wonderful devices. Basically, and I describe them in detail in my salinity video. CTD stands for conductivity, temperature, and density. And it's from conductivity and temperature that we calculate salinity, and then from salinity and temperature, we calculate the density. And we can create a vertical profile and go from there. The World Ocean Database Project is the largest database for temperature profiles from all the oceans. The upper ocean heat content in most North Atlantic regions is dominated by heat transport convergence, a location where ocean currents meet, or the middle of the gyre, which is a convergence zone with subsequent downwelling at the center. And so, we have these convergences. There's not a large change to temperature or salinity. Mixing does occur with some diffusion of heat and salt, but not enough so that individual water masses are still discernible. And we can see this in TS curves or temperature salinity curves. Now, there may be cases where there's a lot more mixing going on, and we have another situation there. Like everything else, you have to go by the circumstances, the conditions of where you're at. But oftentimes, what you see is you can see the blending, but you can still say, we see this water mass and this water mass are the water masses contributing to what we're seeing with the measurements. Okay, now we get into some graphics here. Okay, and this is from NOAA, NES, DIS, NCEI Ocean Climate Laboratory, and it's from Levitas, a 2012 paper. So we see we're going from basically the mid-50s to 2020, 2021. So we're looking at 0 to 700 meters in depth. So it's accumulation. In other words, this integral from 700 to 0 or minus 700 to 0. Okay. That is here. And notice the heat content is 10 to the 22nd joules. Now, 10 to the 21st is a zettajoule. Okay. So you could have said 10 zettajoules, in other words. So if I say 20 times 10 to the 22nd joules. That's basically saying 2 times 10 to the 23 joules, or I can say 200 zettajoules. All mean the same amount of heat. Okay? So the global ocean heat content, now updated through all of 2020, the long-term warming trend is clear, looking at the 0 to 700 meter depth. And here's the URL, ncei.noaa.gov, access global ocean heat content. So what about these lines here? The red line is a 3-month average through October December 2020. That's this here. Okay? So they take 3 months and they average it. So you might go January, February, March, then February, March, April, May, June. You get the idea. The black line is yearly average through 2020. So what's the average over the year? And then the blue line, red line, white background, must be a hockey rink. But the blue line is the pentadal average through 2016 to 2020. In other words, this is a 5-year running average. That's why it stops here at about 2016 or so, because we need to get through the next couple of years to continue the calculation. In other words, it's a recursive calculation. You go back, 2 years. So for example, I can't report, for 1980 until I calculate 76, 77, 78, 79, 80. And then I can't report 81 until I go back to 77, 78, 79, 80, 81. You get the idea. Okay? Actually, for 80, it's 75, 6, 7, 8, 9, and then 6, 7, 8, 9, 80 for 81, and so forth. So that's why, if you look at this, the blue line stops a little bit short of 2020, and the black line is right here, and we see this proceeding into 2021 right here. Little red line just into the beginning of 2021. But what are we seeing here? Okay. We're seeing the heat content increasing. The ocean is absorbing the heat. Here it is. It's right here. It's showing us. Very clear. Very clear. On the next graphic is looking at 2020 ocean temperature, heat content, and we're looking at the upper 0 to 2,000 meters. Again, here's the link, URL for that. Let's take a look at it. Now, the baseline is 81 to 2010 for this graphic here. Now we can see the units of zettajoules, right? 10 to the 21 joules. So it goes from late 50s to 2020. And you see the green vertical bars here? That's the 95% error bar. In other words, the true actual mean is within this interval. Right? So it's within this interval. Now you notice that the error bars become smaller over the years because our ability to measure this has improved greatly. Now, I want to point out something for you. 81 to 2010. Okay, that's a 30-year period here. Okay, so here's approximately 81. So if I was to compute this area here, right, this little blue area, which is below the baseline, and then go to 2010, right, which is about here, and calculate this area here, okay, if I was to do that, they would approximately be the same. Well, since this is below the curve, we would assign this a negative value. Notice a negative algebraic summation, and this would be a positive algebraic summation. But this would pretty much cancel out each other, giving us the average of around 0. The baseline. What this is showing is that Before 81, the oceans were cooler compared to this 30-year period. Now look at this. Starting in about 96, 97 or so, look at all the heat the ocean's been sucking down. Now this is for the upper 2,000 meters. So if I wanted to read this here in 2020, okay, we're looking at that. That's almost 250 zettajoules right there. Not to put too fine of a point on it, that's a shitload of energy. So this is telling you the ocean's absorbing a lot of the heat. So this is just the anomaly. How much above this baseline average? That's a lot. This is very troubling news, actually. Okay. The differences between the 2020 ocean heat content analyses between the two data sets reflect the uncertainties in the calculation due to method and data coverage. Further quantification of the uncertainties in OHC will help to better specify the confidence. Like anything else, okay, that goes back to these error bars. As our methodology improves, as the technology improves, we get better equipment, we will be reducing the error and having better confidence in our values. So we look at the ranking, and what do we see? 2020, 2019, 17, 18, and then 2015. So 2016, okay, see the little drop down here? 2016. This 15, 17, right? So what this is telling us, wrong way, is that these are the warmest years for the ocean. These are the 5 warmest years of the ocean. That look like a trend to you? Sure looks like one to me. So ranked order the hottest 5 years of the ocean since 55. For the upper 2,000 meters in units of zettajoules relative to the 81-2010 average. 5 of the hottest years have been in the past 6 years, 2020 inclusive. This is telling, folks. That's what this table is telling us. Over 90%, 93% of the excess heat due to global warming is absorbed by the oceans. The heat has already penetrated into deep layers. Ocean warming is a direct indicator of global warming and the best measure of the Earth's energy imbalance. Now, the graphic I'm about to show you is, in my opinion, an extremely important one and extremely telling one. So what they're looking at here is they've broken down the ocean into 4 layers of 500 meters thick. 0 to 500, 500 to 1,000 meters, 1,000 to 1,500 meters, 1,500 to 2,000 meters. Okay? What do we see here? Right? And again, this is relative to the 81-2010. We see that, up until pretty much 1990, you got a couple little things here and there. Pretty much up until 1990, the oceans were cooler compared to the baseline. Then, starting about 1990, starts getting warmer and warmer and warmer and really warmer, almost to the point of basically looks like 150 zettajoules above anomaly. Anomaly is zettajoules, right? This is just above the baseline. Look how much, that is an incredible amount of heat. The oceans have been absorbing so much heat that if it wasn't being absorbed would be in the atmosphere. We would probably be extinct already. So we see this here, right? Pretty much almost off the chart here. So now look at the 500 to 1,000. Okay? If you look at this, there's a little bit of a lag, and then it starts warming up. And we get into the, kind of that color, whatever. I don't know what these colors are called, folks. So, but you can look at these graphics and you can call them what you want, but you can see that it's getting darker. Okay? So what this is showing is the heat is diffusing down through the water column, down through depth. And when we get to 1,000, 1,500, we see the same thing. Now, there is a little bit of a lag, okay? And then we see that as the years progress, that more heat's being pulled down, diffusing down, so that it also continues to warm. Now, take a look at this. 1,500, 2,000 meters. Still a little bit of a lag, but now it has stayed at this, I guess that's pink, at this first layer here. This tells me, now it's very possible if we were to play this out into the future, say 2025, that maybe we might see some of, starting to get a little warmer. Maybe more heat is diffusing down, but, right now, looking at the data as is, what this is telling me is that the heat diffusing into this layer here, 1,500, 2,000 meters, is slowing down or maybe has stopped. That is telling me that the thermohaline circulation has slowed down, is slowing down and slowing down dramatically. I mean, we've already measured the slowdown in the deep water formation in the Jin Sea, right, AMOC. We've measured a slowdown in the Gulf Stream. So it would make sense if those are slowing down, so will the thermohaline circulation. Well, remember, thermohaline circulation, the conveyor belt, is a heat distribution mechanism for the planet. So it brings heat from the surface to depth, along with carbon dioxide. Let's not forget that. So if that's slowing down, it's not going to be distributing the heat, because remember, this will flow from the North Atlantic all throughout the oceans, upwelling, some parts upwell in the Antarctic divergence zone, supplying nutrients to that ecosystem, so forth. Here's the other thing I want you to look at. Look at the drastic difference here. Okay, I mean, we're talking, let's see if this is like the third stripe here. So we're talking maybe that's what, 70 zettajoules up to 150 zettajoule. That's a huge disparity. What this is telling me is that we are, in addition to the thermohaline circulation slowing down, we are seeing a massive stratification of the oceans. A massive stratification of the oceans. The ocean's stratified. This is very bad. And I've discussed this in recent videos, why stratified ocean is a terrible situation. Basically, without the vertical mixing, you're not going to get the nutrients mixed into the photic zone for the phytoplanktons to use. They start dying, productivity tanks, food webs, food chains tank, and we have a situation on our hands where the whole marine food ecosystem could collapse. Add to the fact that phytoplankton supply 55 to 80% of atmospheric oxygen. This is why this is an extremely alarming, horrible situation. So this graphic is telling me, the ocean's heated so much that we're seeing massive stratification. We're seeing a slowdown the thermohaline flow. This is pretty much uniform. One other thing to think about. We're seeing what now in the oceans? For example, from the East Siberian Shelf, from, say, the Barents. We're seeing what? We're seeing methane plumes. Now, I am not aware of a study examining this directly, but a hypothesis I have is that the warming ocean water is a major factor, maybe even a leading factor in the methane releases. You warm up the ocean water starts warming up the substrate it interacts with. Just like you warm up the atmosphere, it enables the thawing of the permafrost to take place, which allows methane to be released along with nitrous oxide. Further warms the atmosphere, right, creating a positive feedback loop. To me, I think it's plausible to reason that the increasing water is increasing the substrate temperature, which is then helping to melt the hydrates and clathrates, and then releases the methane in gaseous forms. And I showed you videos from Igor Samolitov's crews where there's these big methane plumes reaching the surface. So not only is this telling me how much heat the ocean absorbs, not only is it telling me the stratification is well underway, not only is it telling me the thermohaline flow is slowing, it's suggesting to me that this warming water is a contributing factor in releasing more methane from the ocean into the atmosphere. And methane gets in the atmosphere, it's a more potent greenhouse gas, may not persist as long, but don't forget, it oxidizes into carbon dioxide. That's why you're starting to see more CO2 equivalents being mentioned in papers. And that ppm is about 560, 565 or so. So this is an extremely important graphic. If you want, pause the video and stare at this, but I've given you my summation, my take on the information that this is relaying to us. So the geopattern of 2020 ocean heat content relative to 8120 shows warming throughout most of the world's oceans, with higher rates of warming in both the northern and southern Atlantic, except southeast of Greenland, because of all the ice melt, and localized zones of the Pacific, Indian, and Southern Oceans. Let's take a look. This is what they're referring to, right? Gulf Stream is right about there, right? So the Atlantic is pretty much warming up. There's that spot off Greenland, all that ice melt right there. Here's what they're talking about, in this, for localized spots in the Pacific, Indian, and Southern Ocean. This is about where you find the Antarctic bottom water coming off. Part of the circumpolar flow there, mixing, and so forth. But you can see, 2020 ocean heat content anomaly at the upper 2,000 meters relative to this baseline, 10 to the 9 joules per square meter. Blue's cooler, dark brown, very warm. So you can see, look at the Arctic Ocean, by the way. Look at the Arctic Ocean. Why is the sea ice disappearing? There's your answer. Look at it. No ice, you can absorb all that heat energy, plus you got flow in through the Bering, flow through the Fram, bringing in warmer water. Yeah, there you go. Now, with WRT, that's a way of saying with respect to 2019, the spatial pattern of 2020 ocean heat content anomalies is much less distinct because internal variability can overwhelm long-term trends, and so causes the heat redistribution in the Pacific and Indian Oceans. North Pacific warming 2020 supports what's called marine heat wave. So basically, what this graphic does is going to compare 2020 against 2019 in the upper 2,000 meters, whereas this one looked at 2020 against this 30-year baseline. This looks at the back-to-back years. That's why they're saying when you look at the long-term trend, it's very dramatic. When you look at year-to-year, not so much, okay? And what we're seeing here, okay, in 2019, I forget what it was, but we had ENSO going on. I know 2020 had a La Nina situation here, so I think that is reflected here. Pacific, and with that, with the warmer waters being pushed westward, we can see it influencing the eastern Indian Ocean and so forth. So this is just an interesting comparison from year to year. Shows you there's a lot of variability, but when you compare the long-term trend, you can clearly see there's a warming pattern going on. It's just like, weather. It varies day to day when you look at climate, which is what? Weather over the long term averaged out. So that's kind of interesting. Ocean heat budget update. A total full depth ocean warming of 380 plus or minus 81 zettajoules. That's the dashed lines. Okay. Represents this error margin. And this error margin can equate to 0.39 plus or minus 0.08 watts per square meter over the global surface. And we're looking at 50 years, 60 years, 1960 to 2020, with about 40.3% in the 0 to 300 meters, 21.6% in 300 to 700 meters, 29.2% in the 700 to 2,000 meters, and 8.9% in the basically below 2,000 meter layers, respectively. What are we talking about here? Let's take a look. Okay, here's the dashed line. That's the basic confidence interval, the error. The light blue is the 0, 300 meters. 300 to 700 is this color blue. Then the little darker blue is 700 to 1,000 meters, and then 2,000 and below. So you can see the error is larger as you went further back in time, and we've now improved our ability to do these measurements, so the error is smaller. So here's the energy in zettajoules. So take this number and multiply by 10 to the 21. So what are these percentages here? If we were to integrate, right, from this here to this point, do an integral of it, basically compute the area of the curve, okay, and then compute the area each of these color regions represents as a percent of the total area, you get these percent values. So now the question is, why is the 300 to 700 meter less than the 700 to 2,000 meters as far as the percent of heat contained? That could be due to a number of factors, including where you find the permanent pycnocline, what kind of mixing, diffusing takes place. There could be other physical parameters, other physical mechanisms at work. But if you were to, if you were to add these two up here, okay, if you would add these two up, there you're talking about what? Basically 62%. So we got 62% of the heat stored in the upper 700 meters. You can think of it that way. So you can use that information along with this information and this information, as well as that. So this graphic, that graphic, that graphic are very important to help us delineate the nuances in the data and to show clear trends. And then when you look at this is basically telling you the ocean heat budget. And by the way, some paper from Cheng et al., 2017. Okay, it was based on this. He updated it to bring us to 2020. So this is the heat, but this is telling you where the heat is. And we can see that 62% of it is basically in the upper 700 meters. Kind of makes sense. Use that in conjunction with the 0 to 500, 500 to 1,000, etc. So 93% of greenhouse gas heat added to the lower atmosphere has gone to the oceans, which makes ocean heat a far better climate change indicator than global average warming. Ocean heat is even penetrating to the bottom of the oceans and increasing there. Remember, in all of this is the specific heat capacity of water. It is much, much higher than air. So you need more energy to increase the temperature of water. So again, if I have a kilogram of water, all right, you need about, 16 joules or so? Yeah, saying 16.7 kilojoules to increase 1 kilogram of water 1C. You won't need that much to increase 1 kilogram of air 1C, far, far less, because water has a much, much higher heat capacity than does air. So you have to keep that in mind. This is when everyone looks at a lot of atmospheric science is looking at the atmosphere. Okay, fine, understandable. Important research needs to be done. You need to look at what's going on with the ocean, because now, because of the high heat capacity, you got all that latent sensible heat energy. This is why I now say that even if thermohaline shuts down, warming is going to continue, where in the past that wasn't necessarily the case. There's just so much energy, as I'm showing you here in this presentation, in the water, just so much energy that all this heat is still going to be given off, and for millennia to come. Okay, so as I said, the prior slides based on Cheng et al. 2017. This is now updated, just published in January 2021. Ocean temperature hit record high in 2020. Here's the total heat. So when you look at this is a percentage of the total heat. And that's what these values represent, the percentage of the total. And it said you can easily calculate that by just doing basic integration. So if I want to know this percent, do upper curve minus lower curve, and then that's a percentage. Very simple mathematics. So, and what we showed is penetrating the bottom of the ocean, but I'm seeing indications that the diffusion, the flow of the thermohaline is slowing down the diffusion, so that I think the heat is slowing as far as reaching the really deep depths. Regional assessment is crucial to risk assessment and societal adaptation. In the tropical North Atlantic Ocean, where hurricanes generate and develop, ocean heat content increases have been persistent since about 1958. The Mediterranean Sea, surrounded by 22 countries, is a hotspot of climate change. What's not included is the equatorial Pacific because of the difficulties in getting out there. So in other words, this is what they've done. And so before we go into each of these boxes, a general view of what's going on. Each of these graphics goes from 1960 to 2020. We're comparing to the baseline, right? And what this is showing is the heat content, right? Joules per square meter. The baseline is 81 to 2010, right? So joules per square meter. And what they're doing is, if I look at this graph here, Northwest Pacific, okay, that's this box here. This box here is the North Indian. Okay? This entire big, huge one here is the Southern Ocean. And we got the Mediterranean Sea. So when you look at this here, each of the little boxes, you can follow the arrows out and look at the section of the ocean. So northeast, Northwest Pacific. Oh, here's the Northeast Pacific. Went down here. There we go. So what this is showing is that the heat content, measured in joules per square meter, is increasing in all the cases except for the Northwest Pacific, which is showing a slight downward trend, which is very interesting. And I think that might be part of some ENSO and the IPO, the Interdecadal Pacific Oscillation. But all the other oceans at which they have data for is showing an overall increase in the heat. So they've got monthly, they've got smooth, and then the shading is the 95% confidence interval, what you see here, right? So this is the monthly, this is the smoothing, right, over the long period, and this blue shading, you can see really dramatically here in the Mediterranean, is the 95% confidence interval. In other words, 95% of the time, the actual value will be within that interval there. So this is kind of showing that this is kind of basically nearly uniform throughout all the oceans. They don't have any data for the Arctic. That would be interesting to see. The salinity contrast increase trend. The fresh gets fresher, indicated in blue, and the salty gets saltier, indicated in red, and that contrast, the increasing, continues, indicating the acceleration of the global water cycle. The ocean vertical stratification continues to increase. I showed that earlier to you, right? This graphic. Okay. And mainly caused by stronger ocean warming at upper layers than deep water. Okay, so what is this showing here? First of all, again, from basically from the mid-50s or so to 2020, the salinity contrast for the upper 2,000 meters, and then the ocean stratification for the upper 2,000 meters. Okay, these are just relative scales here, and what we see is there's a strong correlation. We see that the curves are pretty much the same following it, and what this is showing is that we're seeing the stratification increasing, and this is increasing to, we're seeing a stronger salinity. In other words, take for example, when you have a lot of evaporation, you put the water vapor into the air, what happens to the surface water? The salinity increase because you've removed the water. You have the same amount of salt, but less water. Other areas like the Arctic, where you keep having freshwater dumps, the fresh gets fresher. So you have heard me say before when I discuss things going on land that wet areas will get wetter, dry areas will get drier. Well, basically what this is telling us is that salty regions will get saltier, fresher regions of the ocean will get fresher yet. In other words, in areas that have already high salinity, the salinities will get higher. In areas that have lower salinities, the salinities will get lower. That's what this is telling us. This is a disparity. It's telling us the disparity of, in essence, the water budget. Evaporation versus precipitation patterns. In other words, these are changing. They're changing because the ocean heat is affecting what the ocean is going. Of course, the ocean atmosphere it affects what happens in the atmosphere, right? But 93% of the heat's gone into the ocean. That's going to start affecting things. And that's what this is showing. Salty areas will get saltier. Fresh areas will get fresher. Coupled with the stratification, coupled with changes in the precipitation, evaporation aspects of the global water cycle. In other words, we're talking positive feedback loops here. How do we observe the ocean? Here the plot shows a geographical distribution of the temperature profile data since 1940. Different colors show data observed by different instruments. Okay, not going to break it down for you, but we got 1940 to 59, 60 to 74, 75 to 89, 90 to 2004, 2005 to 2020, and the different colors refer to whatever method was used. For example, I guess it's what? Yellowish orange, orangey yellow, whatever. That is from the CTDs. Black is from drifting buoys. Argo, other instrumentation. So as you can see, we've done a lot of sampling over the years. We even have moored buoys that then send the information up to a satellite that then beams it down to a researcher's computer, and he gets all the data. He doesn't even have to go out in the ocean. He can just analyze the data on his desktop. But you can see we've done a lot of sampling. Some areas that are missed, like the Southern Ocean, it's hard to get to. You can see how sampling has increased over the years. Technology, research time improves, what have you. So this shows you, we've done a lot of sampling, we've done a lot of work, and there's more work still to be done. Now, we mentioned earlier thermal expansion contributing to, the ocean absorbs all this heat energy, the water's going to start expanding. Here are the latest observations of global mean sea level change, basically satellites using altimeters, and from sealevel.colorado.edu. The different colored dots here represent different instrumentations. The black is the 60-day smooth, which you see here. Right? And then the blue, now looks like it might be a straight line to you, but it is not. Quadratic fit. This is the polynomial of second degree. So the average rate is 3.3 plus or minus 0.4 millimeters per year. The acceleration is 0.097 plus or minus 0.025 millimeters per square year. Now you're going to say, what on earth is a square year? This is really an algebraic simplification. To explain this, let's take a position function. When you have a position function, when you take the change in position with respect to time, you get what's called velocity. So let's say a position function is represented in meters. Okay, the change in meters per, say, second. So you have meters per second. Change in position gives you velocity expressed in meters per second. But what is a change in velocity? You have the velocity is already meters per second, but now you're going to want to know, how does the velocity itself change per second? So you have meters per second, which is velocity, and that is changing itself with respect to every second. So you get meters per second, which, by the way, is called acceleration. Meters per second, when you simplify it algebraically, it becomes meters per second square. So what this is saying is that the average rate is millimeters per year, and then the rate itself, acceleration, is changing per year. So it's millimeters per year per year. In other words, what this is telling us is that quadratic fit, that means it's exponentiating. So the change itself, the acceleration in the rise of the sea level itself is accelerating. That is alarming. Let me repeat that again. We fit a quadratic function to this data. Quadratic is not linear, not constant. Quadratic is basically polynomial of degree 2. It's exponentiating. In essence, not a true exponential function, but when you have a polynomial that is degree 2 or higher, you're going to have a rapid increase. What this is telling us is that the level of sea level change, the rising sea level change itself, is accelerating. It's not constant. That's what this is telling us. Now, when you compare from 1995 to, say, 2020, and that looks like 60, and then we have minus 20, say 1, that means sea level, according to this, has increased by 81 millimeters. 81 millimeters is 8 centimeters, 8.1 centimeters. That may not seem like a lot, but that's a lot in such a short time span. I mean, we're talking, what, 25 years? So this is 3.3 millimeters per year, and it's accelerating. Think about that. So, what this is showing us is the oceans are really absorbing the heat, much more so than the atmosphere. And a lot of the heat the atmosphere has absorbed has gone to melting the ice and increasing water temperature. But a lot of that ocean heat, a lot of that heat energy we put into the atmosphere has gone into the ocean, which is then warming the waters. And when you consider the specific heat of water being so much higher than air, that is a lot of energy that has increased the measured changes that I've shared with you, like when I examine sea surface temperatures with you guys. Right? We've seen how much warmer it has gotten. Well, now I'm showing you integrated over depth down to 2,000 meters, and look at the energy content, 200 zettajoules or more. That is a tremendous amount of energy. And as I showed you earlier, a lot of that heat is in the 62% of it is in the upper 700 meters. But when I broke it down to you in 500 meter intervals, 0 to 500, 500, 1,000, so forth, I'm showing you drastic stratification is underway, a slowdown in the thermohaline flow. There's still heat diffusing down, but it is slowing down. And we're leading us to a stratified ocean, which is not good. There is a lot of heat energy in the water, a lot of latent and sensible heat energy. This is extremely troubling to see this rapid stratification underway. As explained in other videos, and I mentioned earlier, stratified oceans is not a good thing for the planet, not a good thing for humans, not a good thing for organisms. We're already in the middle of a mass extinction event. Looks like it's going to continue. So, yes, I know it's a lengthy presentation. I hope you found it informative. I hope it gave you a lot of things to think about and to contemplate as we go from here on out. I appreciate your patience, and I thank you for your time, and we'll talk soon. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.